Welcome to the Deep Dive. This is where we take a stack of sources, the articles, the research, the private notes, and extract the most important nuggets of knowledge and insight, giving you a shortcut to being truly well-informed.
And today we are deep diving into a figure whose life story wasn't just central to the revolution of atomic physics, it was the revolution.
We are charting the path of Niels Henrik David Bohr, a man whose existence spanned from the late Victorian age straight through to the terrifying birth of the nuclear era, forcing the world to rethink reality itself.
And that's exactly the intellectual terrain we need to cover. When we analyze the sources about Bohr, we aren't just looking at the work of a brilliant physicist. We're looking at a philosopher, an institution builder, and a humanitarian.
So our mission for you, the listener, is to really extract the core insights that reveal the scope of his impact.
Right. From his pivotal stabilizing model of the atom, which fundamentally changed our mental picture of matter, to his most enduring philosophical concept, complementarity, which attempted to tame the genuine absurdity inherent in the quantum world.
Bohr's list of achievements is immense, so let's maybe set the stage quickly with his foundational contributions.
His work is truly foundational. First and foremost, he received the Nobel Prize in Physics in 1922.
And that was for his work on atomic structure.
Specifically, for his investigations into the structure of atoms and the radiation they emit. This was a direct result of his development of the Bohr model, which was this huge paradigm shift.
It introduced the whole notion of discrete electron energy levels and these stable quantized orbits around the atomic nucleus.
Exactly.
That model, though eventually surpassed, is the reason we picture the atom the way we do, a little solar system of electrons orbiting a central core. It really solidified the image of the atom for the entire 20th century.
That visibility is important, but intellectually, the deep legacy lies in his philosophical framework. That is his conception of complementarity.
And this isn't just a physical rule, right? It's a way of thinking.
It's a philosophical methodology. It posits that to understand certain phenomena fully, you have to analyze them in terms of apparently mutually exclusive or contradictory properties.
The classic example being the wave and particle behaviors of light and matter.
The most famous pairing? Yes.
Yeah.
The sources confirm this was the framework through which he processed both science and really life.
And finally, his legacy as an organizer cannot be overstated. He founded the famous Institute of Theoretical Physics in Copenhagen,
Now the Niels Bohr Institute.
which became the global hub, the nerve center for quantum research and debate throughout the critical decades of the 1920s and 30s.
It wasn't just a building. It was a sanctuary and a forge for the greatest scientific minds. It allowed the European scientific community to focus on these revolutionary ideas, giving them a physical, collaborative space to argue and synthesize.
Okay, let's unpack this. Before we get into the quantum leaks and the nuclear secrets, we have to start where many great minds start, but perhaps not where you'd expect for a theoretical physicist.
On the football field.
Exactly, on the football field.
Well, it's vital to place Bohr within his early context. Niels Bohr was born into a highly cultivated intellectual environment in Copenhagen. His father, Christian Bohr, was a respected professor of physiology at the university.
So Niels grew up surrounded by high-level scientific and philosophical debate.
Constantly. And his mother, Ellen Adler, came from a wealthy and prominent Danish-Jewish banking family, which provided both cultural depth and financial stability, which was crucial for his later academic pursuits.
What's truly surprising is the immediate family talent. I mean, it wasn't just Niels who excelled on a global stage.
Not at all. His younger brother, Harold Bohr, became a famous mathematician, but he was also an elite athlete.
An Olympic footballer. He won a silver medal with the Danish national team at the 1908 Summer Olympics.
And Niels shared that passion for the sport. The sources indicate he's a dedicated footballer, playing goalkeeper for the Akademisk Bold Club, the academic football club, in Copenhagen.
He wasn't quite at his brother's Olympic level, but still the image is striking. A mind focused on the most abstract concepts in the universe, also demanding the visceral, high-stakes physical discipline required of a goalkeeper.
It really suggests a lifelong comfort with rapid transitions between intense mental focus and practical, real-world engagement.
That duality, the philosopher and the practical operator, becomes the theme of his life. But his scientific genius started manifesting undeniably during his undergraduate years at the University of Copenhagen.
Oh, absolutely. He was immersed in physics, astronomy, mathematics, and philosophy. But the pivotal moment of his early scientific acuity came in 1905, with the competition for the Royal Danish Academy of Sciences and Letters gold medal.
Tell us about the task. This sounds like some academic hurdle, but it quickly became a test of extreme dedication and precision.
It was incredibly demanding. The challenge was to investigate a method first proposed by the British physicist Lord Rayleigh back in 1879.
So an old problem.
An old, unsolved problem. The goal was to measure the surface tension of liquids by measuring the frequency of oscillation of a water jet radius. It required incredibly delicate, precise experimental work.
And the university notoriously lacked a proper modern physics laboratory.
Exactly. So Bohr set up his experiment in the best place available, his father's physiology laboratory. Think about the commitment required here. He wasn't just theorizing, he was conducting meticulous, long-running experiments.
I read he had to make his own equipment.
He did. To achieve the required accuracy, he had to blow and shape his own specialized glassware, specifically test tubes with elliptical cross-sections, to properly analyze the oscillations.
So he wasn't just following instructions, he was improving the tools themselves.
And he didn't stop at the experiment. He dramatically refined the theory. Rayleigh's original proposal had not accounted for the viscosity of the water, nor had it dealt with oscillations of finite amplitudes. It was, simplified, assuming idealized conditions,
Bohr corrected Rayleigh's theoretical framework.
factoring in water viscosity and working with real-world finite amplitudes.
So he took an established 19th century theoretical framework, spotted its flaws, corrected them both mathematically and experimentally, and built the custom equipment required to prove his corrections. That's an extraordinary feat for a young student.
It really shows his unique ability to engage with both the deepest theoretical principles and the grittiest practical details of experimentation. He submitted his essay at the very last minute, a classic academic move, and won the gold medal.
A massive validation.
A huge validation of his capacity for meticulous work and theoretical correction.
And that ability to spot the fundamental shortcomings in established theory became the signature move of his entire career. But, his foundational work in his 1911 PhD thesis on the electron theory of metals faced a frustrating non-scientific limitation.
This is a perfect example of how non-scientific barriers can impede the flow of world-changing ideas. His thesis was based on extending the then-current gas-like electron model developed by Paul Drude and Hendrik Lorentz.
He applied Lorentz's model rigorously and critically concluded that it failed.
Utterly. It could not possibly account for basic observed phenomena like the Hall effect or the magnetic properties exhibited by metals. He saw the wall that classical physics was about to hit.
Precisely. The thesis was groundbreaking, identifying the inherent limits of classical electrodynamics before the quantum revolution had fully taken hold. Yet it was ignored.
Because the University of Copenhagen required it to be written in Danish. It was virtually ignored outside of Scandinavia, and this led to a historical injustice.
Hendrika Johanna van Leeuwen.
Over a decade later, she independently derived the exact same theorem about the failure of classical mechanics to explain the magnetic properties of matter.
And now that result is known as the Bohr-van Leeuwen theorem. He was a decade ahead, but isolated by language. That must have been a powerful lesson for him about the absolute necessity of universal communication in science.
It certainly underlined the need to engage internationally. Supported by a fellowship, Bohr left Denmark in 1911 to seek out the cutting edge of global physics in England.
So Bohr initially sought out J.J. Thomson at Cambridge. This is the man who had discovered the electron and established the plum pudding model of the atom. Why was this initial partnership a failure?
Well, Thomson at that point was deeply invested in his own model, a diffuse, positively charged sphere embedded with electrons, like plums in a pudding.
And in walks Bohr.
In walks Bohr, a young, somewhat awkward foreign academic eager to discuss his PhD thesis that essentially concluded Thomson's classical models were fundamentally limited. Bohr failed to make a strong connection, and Thomson, busy with his own work, likely just dismissed the young man's radical conclusions.
So the intended mentorship failed, but here's where it gets really interesting. Bohr quickly pivoted and found his true intellectual partner in Ernest Rutherford, based in Manchester.
And Rutherford had just fundamentally redefined the atom with his 1911 experiments.
The gold foil experiment.
Right, which demonstrated that the positive charge and nearly all the mass of the atom were concentrated in a tiny, dense central nucleus. This was the nuclear atom, a massive leap beyond the plum pudding.
But the nuclear atom, in Rutherford's time, presented a catastrophe for physics, didn't it? I mean, it shouldn't have been stable.
It presented an impossible contradiction. Classical electromagnetism, specifically Maxwell's equations, dictated that any electron orbiting a central nucleus must continuously radiate energy,
And by radiating energy, the electron would rapidly lose velocity?
spiral inward, and collapse into the nucleus in a fraction of a second. According to established, proven physics, atoms shouldn't exist. They should be completely unstable.
So Rutherford provided the structure, but classical physics insisted on instant atomic collapse. This was the crisis Bohr had to resolve.
And he resolved it by executing what we now recognize as the ultimate conceptual fusion. He took Rutherford's physically verified structure and grafted onto it Max Planck's recently introduced deeply disruptive quantum theory.
Planck had suggested that energy could only be absorbed or emitted in discrete packets, or quanta.
Exactly. And this fusion culminated in his famous trilogy, the 3 papers published in Philosophical Magazine in 1913.
So what were the core radical ideas he introduced in those papers?
There were 2 major breaks from classical tradition. First, Bohr postulated that electrons only exist in specific, fixed orbits called stationary states.
And in these orbits, contrary to classical prediction, the electrons do not radiate energy.
Thus stabilizing the atom indefinitely. Second, he asserted that electrons move between these fixed orbits. They don't spiral by absorbing or emitting a single discrete quantum of energy, which corresponds exactly to the energy difference between the 2 states.
That idea, the quantum jump, was revolutionary, and it formed the foundation of the old quantum theory. But the true power, as we always look for in science, is predictive capability.
Absolutely. The immediate, stunning validation came from the hydrogen spectrum. Since 1885, Johann Balmer had derived a simple, elegant mathematical formula, the Balmer series, that accurately described the visible light emitted by hydrogen atoms.
But for 30 years, no one could explain why that formula worked. It was just a mathematical observation without a physical foundation.
And Bohr provided the foundation. Using the structure of his new quantum model and employing only fundamental constants, the electron mass, its charge, the speed of light, and Planck's constant Bohr was able to mathematically derive the Rydberg constant and Balmer's entire formula from first principles.
He took an empirical observation and anchored it in fundamental physics.
That level of success was unprecedented.
That must have been the moment the scientific world realized this wasn't just a clever fix, this was a total intellectual reset.
It was a monumental achievement, and it immediately stood up to challenge. When astronomers pointed to the Pickering series, spectral lines observed in stars that didn't fit Balmer's formula, Bohr's model quickly explained them
As wedge.
as being caused by ionized helium, a helium atom that has lost 1 electron, leaving it with a single electron orbiting the nucleus, which mimics the physics of hydrogen. His model successfully predicted and explained this unexpected data.
But despite the predictive success and the elegance Einstein referred to as musicality, there was resistance. You mentioned the older guard.
The resistance was profound, particularly among those physicists whose careers were built on classical determinism, J.J. Thomson, Hendrik Lorentz, and others. The idea of quantum jumps, these non-deterministic transitions between states, was horrifying to them.
It violated their deepest intuitions about the smooth, continuous nature of reality.
Absolutely. However, the younger generation, Einstein, Rutherford, Max Born, they recognized the power of results. It was the model's ability to explain long-standing mysteries and accurately predict experiments that won the day, regardless of philosophical discomfort.
So the revolution was won not by theory alone, but by a combination of profound theoretical intuition and experimental validation. By 1916, Bohr was back in Copenhagen, recognized as a global leader.
His stature was such that he was appointed to the chair of theoretical physics. This allowed him to focus on his next major contribution, institution building. Beginning in 1917, he tirelessly campaigned to establish the Institute of Theoretical Physics.
What made the institute so unique?
Its scope and its funding model. Bohr successfully secured financing not just from the Danish government and the esteemed Carlsberg Foundation, but significantly from industry and private donors, many of whom were from the Jewish community, reflecting his mother's background and his broad network.
So when it opened in 1921, it wasn't just a university department.
Not at all. It was designed to be an international hub. He transformed Copenhagen into the intellectual capital of the quantum world.
He created a unique culture there, from what I've read.
A completely unique culture. It wasn't formal lecture halls. It was intimate, demanding debate, fueled by collaboration and a shared sense of revolutionary discovery. The Institute became a magnet for every brilliant young physicist of the era. Hans Kramers, Oscar Klein, Wolfgang Pauli, Werner Heisenberg, and others.
The group, the Copenhagen School, essentially defined the interpretation of quantum mechanics for decades.
You could argue that the creation of that environment, a place where debate was fierce but mentorship was total, is arguably as important as his papers.
So the Bohr model achieved the Nobel Prize and stabilized hydrogen. But as we move past the simplest atom, the model began to strain. The sources show that the quantum world is infinitely more complex than a neat solar system.
That's the reality. The model struggled significantly with multi-electron systems and with incorporating relativistic effects. This led to a major challenge, ordering the periodic table. The classification problem was acute, particularly concerning the rare earth elements, which seemed chemically indistinguishable.
But quantum theory, specifically the work being done at the Institute, offered a theoretical solution to this chemical mess.
It did. By 1924, supported by emerging theoretical concepts, most importantly, Wolfgang Pauli's exclusion principle Bohr made a major scientific prediction that had enormous real-world implications.
He declared that the unknown element 72 was not a rare earth element, as many chemists assumed.
But that it structurally had to be zirconium-like, fitting into a completely different column of the periodic table.
This was a theoretical throwdown. He was betting the principles of the new quantum mechanics against empirical chemistry.
It was high stakes. The French chemist Georges Urbain was already claiming he discovered element 72, which he called celsium, and he insisted it belonged with the rare earths.
And Bohr was confident that quantum shell theory dictated otherwise.
He was. So Dirk Koster and George de Hevesy, working at the Institute, took on the task of finding it. And knowing the predicted chemical similarities to zirconium, drastically narrowed their search. They knew where to look.
And they found it where Urbain wasn't looking.
Exactly. They analyzed mineral samples from Copenhagen's Museum of Mineralogy, and their X-ray spectroscopy confirmed the existence of element 72, proving Bohr correct. They named it hafnium, after the Latin name for Copenhagen, hafnia.
So the discovery of hafnium was far more than just naming a new element.
It was a colossal experimental validation of the new quantum principles governing electron shell filling. It showed that quantum theory was the new, necessary ordering principle of the atomic world.
Yet, despite that success, the pressure to find a smooth transition, a bridge, between the familiar classical world and the radical quantum world was immense. This pressure led to the infamous and ill-fated Bohr-Kramers-Slater theory.
The BKS theory in 1924.
Right, BKS.
BKS represents one of the most radical intellectual gambits in the history of science, born out of frustration. It was an attempt to maintain classical wave concepts while incorporating some quantum restrictions.
And the problem was that they couldn't make it work mathematically or quantitatively.
Right, so it was published more as a program for research rather than a finished theory.
What was the truly radical, even heretical idea at the core of BKS?
The sources reveal that the core idea proposed by Bohr's student Kramers and the American physicist John Slater was that momentum and energy might only be conserved statistically.
Statistically, across many interactions rather than absolutely in every single one.
Yes.
Wait, so they were suggesting abandoning the absolute law of conservation of energy at the atomic level, one of the most bedrock principles of all physics.
That's the magnitude of the intellectual leap they were willing to make to save the picture of continuous classical waves. They proposed that a single photon emission might not strictly correspond to a single electron jump, but rather that atoms emitted and absorbed energy and momentum probabilistically.
That's astonishing. How long did this attempt to save classical reality last?
Not long at all. The sources refer to its refutation as a speedy funeral.
A speedy funeral, I like that.
Experiments were conducted by Walther Bothe and Hans Geiger, yes, the Geiger of the Geiger, counter specifically to test the conservation laws in individual photon-electron collisions.
And their results?
They definitively proved that momentum and energy were conserved absolutely in every single interaction. BKS was dead almost upon arrival. Bohr, acknowledging the failure, instructed his colleague to give their revolutionary efforts as honorable a funeral as possible.
That failure, the utter impossibility of creating a neat classical bridge, must have been deeply significant. It forced the physicists to confront reality as inherently paradoxical.
Exactly. The failure of BKS paved the way for the true quantum revolution. The development of matrix mechanics by Born and Heisenberg, and wave mechanics by Schrödinger. And this failure coincided precisely with overwhelming experimental evidence, confirmed by 1927 that light, and even matter like electrons, behaved as both waves and particles.
You could design an experiment to measure its wave nature, or design a different experiment to measure its particle nature, but never both simultaneously. And this is the moment Bohr conceived the philosophical principle of complementarity.
It was a moment of profound synthesis. Bohr realized that this wasn't a flaw in our measuring tools or gap in our theory, but a fundamental truth about reality. Items must be described in terms of apparently mutually exclusive properties, depending entirely on the experimental setup.
Wave and particle descriptions are complementary.
Both are required for a complete picture, even though they contradict each other in classical terms.
This philosophical principle was developed in close concert with Heisenberg's simultaneous work on the uncertainty principle. How did Bohr refine or challenge Heisenberg's initial conclusions?
Well, when Heisenberg first developed the uncertainty principle in February 1927, he did so using a famous thought experiment involving a gamma-ray microscope. Heisenberg's initial explanation suggested that the act of measurement disturbed the electron, preventing us from knowing its position and momentum simultaneously.
And Bohr saw this as too limiting. It seems like a massive concession already.
Bohr believed it implied that the electron had pre-existing definite properties that the measurement simply messed up. Bohr pushed for a much more radical conclusion, which he presented at the Como conference later that year.
And what was his conclusion?
He argued that the property, position, or momentum could not be discussed at all outside the specific context defined by the measuring apparatus. The system and the instrument form an inseparable whole.
So it's not that we disturb the property, it's that the property doesn't achieve definition until the entire experimental context is established.
Precisely. Bohr even demonstrated that Heisenberg's uncertainty relations could be derived from classical optics, emphasizing that the inability to define both simultaneously was intrinsic to the way we interact with and describe phenomena, not merely a practical problem with a gamma-ray microscope.
He realized the question was moving beyond physics into the very nature of language and philosophy.
It had to.
When Bohr introduced complementarity, he moved from being a physicist to being one of the 20th century's most significant philosophical thinkers. Werner Heisenberg famously noted that Bohr was primarily a philosopher, not a physicist. Where did this deep philosophical inclination originate?
Well, while his formal background was scientific, the sources confirm he had a keen interest in literature and philosophy from a young age. Critically, he read the major Danish Christian existentialist philosopher Søren Kierkegaard.
Right, I read that in 1909, Bohr sent his brother, Harold, Kierkegaard's work, Stages on Life's Way.
And he called it one of the most delightful things I've ever read.
Kierkegaard's philosophy often deals with absolute choices, paradoxes, and the leap of faith concepts that, while religious, structurally resemble the forced choice between complementary descriptions in physics.
That's the structural link some biographers draw. Though Bohr was an atheist and often disagreed with Kierkegaard's explicit Christian advocacy, which is likely the disagreement the sources mention, the structure of dealing with mutually exclusive concepts, like the tension between the aesthetic life and the ethical life, may have provided a framework for Bohr to process scientific paradox.
The real philosophical crux of the Copenhagen interpretation, however, is Bohr's insistence on using classical concepts to describe the quantum world. If the quantum world is so radical, why chain ourselves to the language of Newton? Doesn't that fundamentally limit our ability to communicate the truth?
That is the essential challenge. And Bohr's response is robust, deeply rooted in epistemology, the study of knowledge itself. Bohr believed that for human beings to communicate and gain shared understanding, the account of all experimental evidence must be expressed in classical terms.
Things like space, position, time, and momentum.
The language refined by classical physics.
Yes. Why are those concepts non-negotiable?
Because they are refinements of ordinary language, and ordinary language is built into our very experience of the world. Bohr argued that the word experiment itself refers to a situation where we can tell to others what we have done and what we have learned. If you cannot express the setup and the result in unambiguous language, you have not communicated a finding. And for Bohr, that unambiguous language is provided only by the terminology of classical physics.
So the constraint isn't physical, but linguistic and communicative. We're constrained by our own shared reality.
Exactly. It's a statement about the limits of human cognition and communication, not the limits of reality itself. Now, this focus on description often led to misunderstandings. It's critical to note that Bohr was not a subjectivist or a positivist who believed the atom was merely an idea in the mind of the observer.
He believed the atom was real.
Scholars generally agree Bohr believed the atom was absolutely real.
So he believed the atom was real, but he rejected the idea that we could have a literal picture of it, correct?
That's the tension he navigated, and it leads us to his indefinability thesis. Let's break that down for you. The indefinability thesis simply states that the truth conditions for assigning any precise value, whether position or momentum, to an atomic object depends entirely on the specific apparatus and the outcome of the experiment.
Okay, so if I measure the momentum, the position becomes undefined, not because I disturbed it, but because the experimental setup I chose makes the concept of precise position irrelevant or impossible to define within that context.
That's the heart of it. The property is only definable in relation to the specific measurement context. This also led to his acceptance of the Born statistical interpretation. The T-psi function, a wave function, which describes the quantum state, has only a symbolic meaning.
It represents the probabilities of outcomes, not a literal pictorial representation of reality.
Exactly. And because he saw the Tosi function as symbolic, not a physical wave, that means he couldn't have believed in the literal collapse of the wave function.
That's a crucial distinction often missed.
Bohr never endorsed the idea of a physical collapse. Since the wave function is symbolic, a tool for probability calculation, there is no physical wave to collapse during measurement. He was, in essence, a phenomenological realist. Reality exists, but our accounts of it are constrained by the tools and language necessary for observation and communication.
This rejection of a deterministic, pictorial reality brought him into famous, decades-long philosophical arguments with Albert Einstein.
It's the ultimate intellectual rivalry, always conducted with immense respect and good humor. Einstein, who famously said God does not play dice, preferred the determinism of classical physics and constantly sought to devise thought experiments that would expose a hidden deterministic layer beneath quantum mechanics.
He wanted to prove that the electron had a definite position and momentum independent of observation.
And Bohr, time and again, demonstrated how even Einstein's brilliant thought experiments, like the famous lightbox idea, implicitly contained the elements of quantum mechanics that proved the uncertain key relations held true. He was consistently successful in showing that Einstein's proposed challenges, when rigorously analyzed, ultimately failed to prove determinism.
Bohr championed the necessity of probabilistic quantum physics, while Einstein continued to search for a deeper deterministic theory.
The sources confirm the debate lasted until Einstein's death, establishing the philosophical battleground for quantum theory, the ultimate clash between the old order and the new.
But as the 1930s began, the nature of conflict shifted, and Bohr's intellectual battlefield turned into a physical one, the rise of Nazism and the coming of war.
As the decade progressed, Bohr's Institute became a sanctuary. Throughout the 1930s, as the Nazi regime escalated persecution in Germany, Bohr dedicated enormous personal and institutional effort to humanitarian causes, specifically assisting refugee scholars.
He used his international standing and organizational genius to create a vital lifeline for those fleeing persecution based on their Jewish heritage or their political descent.
He was a master networker and fundraiser. He leveraged his access to grants, notably funds from the Rockefeller Foundation. He provided temporary employment at the Institute, offered direct financial aid, and tirelessly worked his network to find permanent academic positions for these refugees across the world.
The roster of people he helped reads like a list of Nobel laureates and influential minds.
James Franck, Lise Meitner, Edward Teller, Victor Weisskopf, Max Delbruck, the list goes on.
That's an incredible act of moral leadership, using his scientific institution as a bulwark against fascism. And there's an extraordinary anecdote from the German occupation of Denmark in April 1940 that underscores his personal commitment.
The story of the Nobel gold medals is iconic. Two Nobel laureates, Max von Laue and James Franck, both Jewish academics, had smuggled their gold medals out of Germany to Copenhagen to prevent the Nazis from seizing them.
And after the Germans occupied Denmark, Bohr realized the medals were in grave danger of discovery.
Right, which could implicate both the medal owners and the Institute.
So what did they do?
Bohr instructed chemist George de Hevesy to dissolve the metals in aqua regia, a volatile, highly corrosive mixture of nitric and hydrochloric acids. The gold dissolved completely into a hidden solution, effectively neutralizing the physical evidence of the metals.
He hid them in plain sight.
De Hevesy placed the beaker containing the gold solution high on a shelf in a laboratory cabinet. After the war ended in 1945, de Hevesy returned, found the solution undisturbed, precipitated the gold back out, and the Nobel Foundation was able to restrike the original medals.
It's an act of loyalty, defiance, and incredible scientific resourcefulness.
It speaks volumes about the ethos of the Institute. However, the most controversial chapter of the war involving Bohr centers on a meeting that took place in occupied Copenhagen in September 1941 with his former protege, Werner Heisenberg.
Who was, at that point, leading the German nuclear weapons project.
Correct.
This meeting has generated entire historical debates and dramatic works. We must present the conflicting accounts neutrally. Let's start with Heisenberg's version, published later in 1957.
Heisenberg's account was that he traveled to Copenhagen, risking the journey, specifically to communicate the views of several German scientists who felt a profound moral responsibility. He intended to signal to Bohr that while the production of a nuclear weapon was theoretically possible, it would require such enormous effort that scientists on both sides should maybe try to slow down the process.
And according to Heisenberg, Bohr immediately terminated the conversation, shocked and suspicious.
That's his version. But Bohr's recollection, which came to light through draft letters he never sent, paints a much darker picture of Heisenberg's intentions.
Bohr's version recalled being shocked that Heisenberg seemed to encourage cooperation with the Nazis and that Germany was vigorously pursuing nuclear weapons under his leadership. He remembered that Heisenberg's opening remarks suggested the possibility of atomic weapons and that Heisenberg seemed fully engaged in the pursuit.
And then there's a third view, from Heisenberg's student Ivan Supek, who suggested the goal may have been to persuade Bohr to mediate a peace settlement between Britain and Germany.
Which seems incredibly ambitious and naive if true.
To say the least. The released documents show the immense gulf in their understanding of that conversation. The meeting remains an enigma, but the outcome was clear. Bohr became convinced that the German nuclear project was moving forward.
And that conviction was critical. By September 1943, the situation for Bohr, whose mother was Jewish, became critically dangerous. He and his family received an urgent warning that the Nazis considered them Jewish and were planning imminent arrest.
This triggered the dramatic escape from Denmark. The Danish resistance network was instrumental. Bohr and his wife escaped by sea to Sweden on September 29, 1943.
And immediately upon arrival, he used his unparalleled international prestige to meet with King Gustav of Sweden.
And he persuaded him to publicly offer asylum to Jewish refugees fleeing Denmark. That public announcement was broadcast by Swedish radio on October 2nd. This acted as a major catalyst for the heroic mass rescue effort, where Danish citizens mobilized boats and smuggled over 7,000 Danish Jews across the narrow sound to safety in Sweden.
So Bohr's personal intervention was a direct, decisive factor in saving thousands of lives.
Without a doubt.
From the relative safety of Sweden, he was urgently needed by the Allies, who were moving forward with their own bomb project. His final leg of the escape, the journey to Britain, reads like a thriller.
It was life or death. In October 1943, Bohr was airlifted out in a high-speed, high-altitude de Havilland Mosquito bomber, an unarmed plane that relied on speed to evade German fighters.
And he had to ride in the bomb bay.
Lying on a mattress in the bomb bay, using the codename Nicholas Baker, equipped with a parachute and an oxygen mask.
And he nearly didn't survive the flight.
A truly terrifying, near-fatal incident. Because the custom-made flying helmet he was issued was too small, he couldn't wear it properly. This prevented him from hearing the pilot's instruction over the intercom to turn on his oxygen supply when the bomber climbed to high altitude.
He passed out.
He passed out entirely from oxygen starvation and only revived when the plane began descending over the North Sea as they approached the British coast. Had the flight been longer, the quantum revolution might have lost its greatest philosopher.
After that harrowing journey, he and his son, Bohr, using the codename James Baker, were immediately inducted into the British Tube Alloys Project and then joined the British mission to the Manhattan Project in the United States.
Bohr was initially kept out of the deepest technical loop, but his presence was transformative. He visited the secret city of Los Alamos, New Mexico, where the bombs were being designed. Robert Oppenheimer, the project director, credited Bohr with acting as a scientific father figure to the younger men,
providing moral and intellectual clarity amidst the chaos of creation. Richard Feynman, for instance, spoke of Bohr's profound influence during his time there.
He did.
Did he make any concrete technical contributions, or was his role purely advisory and philosophical?
He was certainly advisory, but the sources confirm he made at least one crucial technical contribution late in the project. Oppenheimer credited him with clarifying a specific, complex puzzle related to the design of the modulated neutron initiators in early 1945.
Those were essential components used to trigger the nuclear chain reaction precisely.
Yes, so his decades of experience in nuclear physics were still vital.
But his focus quickly shifted away from the technical details of making the bomb to the overwhelming moral and geopolitical implications of its existence. He immediately recognized that nuclear weapons fundamentally changed international relations forever.
He grasped the implications instantly. Having maintained correspondence with Soviet physicist Peter Kapitsa, Bohr realized that the Soviets were likely aware of the Anglo-American project and would inevitably develop their own weapons. He saw a terrifying and inevitable arms race coming.
And his solution was radical for wartime, the open world concept. He advocated for sharing the project's scientific knowledge with the Soviets immediately.
His reasoning was that secrecy would only fuel suspicion and hasten the arms race. Transparency, he believed, was the only viable path to establishing international control and peace. He met with Prime Minister Winston Churchill on May 16, 1944, to push this idea.
And Churchill's reaction was legendary in its hostility.
Churchill was violently opposed. He wrote that Bohr ought to be confined or at any rate made to see that he is very near the edge of mortal crimes.
Wow.
The political fear of espionage and Soviet power was simply too strong to accept Bohr's abstract argument for scientific transparency.
Despite this stunning political rejection, Bohr went on to meet with President Franklin D. Roosevelt in August 1944.
Roosevelt was initially more polite and sympathetic, suggesting Bohr seek British agreement first. But when Churchill and Roosevelt met at Hyde Park in September 1944, they definitively rejected the idea of sharing information.
They even added a disturbing writer to their memorandum, instructing that inquiries should be made into Bohr's activities to ensure no information was being leaked.
Especially to the Russians. The political leadership simply could not accept the notion that the age of secrecy was over.
Yet, despite being utterly rejected by the two most powerful wartime leaders, Bohr never abandoned the mission.
Not at all. His advocacy continued long after the war. In June 1950, he addressed a famous open letter to the United Nations, repeating his call for genuine international cooperation on nuclear energy. This persistent moral lobbying, an appeal to reason over secrecy, eventually contributed years later to the formation of the International Atomic Energy Agency, the IAEA.
His life perfectly illustrates the intersection of pure science and urgent global geopolitics.
It really does.
After the war ended in 1945, Bohr returned to Copenhagen and dedicated the rest of his life not only to research but to rebuilding the global infrastructure of science. He became a post-war institution builder.
He was central to the creation of what we now call European big science. He was instrumental in the establishment of CERN, the European Organization for Nuclear Research. This was a challenging political process, as multiple nations vied to host the massive new facility.
How important was Bohr's role in securing CERN?
His influence was critical. Some figures initially worried that Bohr and his Copenhagen Institute might be past their prime. However, Bohr realized that continental cooperation was paramount. He eventually threw his crucial support behind Geneva as the main site for the huge experimental facilities.
But he made sure his institute stayed involved.
Oh yes, he successfully negotiated to ensure that the CERN theory group was temporarily based in Copenhagen and his institute until their permanent facilities in Geneva were ready in 1957. Victor Weisskopf, who later directed CERN, emphasized that the support of a figure of Bohr's stature was absolutely essential for the project's success.
And he continued to build up Nordic science as well.
Yes. He chaired the founding of the Nordic Institute for Theoretical Physics in 1957 and became the first chairman of the research establishment RISET in 1956, Denmark's National Atomic Energy Research Center. He ensured that the tradition of collaborative, transparent scientific inquiry continued in Scandinavia and across Europe.
Given this immense scientific and political service, his personal and national recognition was vast. He received the Order of the Elephant in 1947, a deeply prestigious Danish honor.
That's right. King Frederick IX conferred the order, an honor typically reserved for royalty and heads of state. It was a national acknowledgement not just of Niels Bohr the man, but of Danish science's preeminence on the global stage.
And that leads us to his famous coat of arms designed for the award, which powerfully encapsulates his entire philosophical life.
For the Order of the Elephant, the recipient designs their own crest. Bohr's choice was breathtakingly meaningful. His coat of arms prominently features the Taijitu,
The stylized yin-yang symbol.
representing the harmony and interrelation of opposites.
Why choose that specific symbol, a Chinese philosophical symbol, for a Danish coat of arms?
Because the Taijitu perfectly visualizes complementarity. It shows two apparently opposite forces, yin and yang, that are not antagonistic but mutually defining and necessary for a complete whole. This was the exact framework he developed to understand wave-particle duality.
And beneath the symbol, he placed his personal Latin motto, Contraria sunt complementa.
Opposites are complementary. He literally etched his quantum philosophy into his national identity.
It was a profound self-summary, synthesizing the highest honor with his deepest intellectual insight.
It really was. And his scientific legacy, of course, continues into the elemental names. The synthetic element with atomic number 107 is named Bohrium and astronomical honors, including an asteroid and a lunar crater. He died in Copenhagen in 1962 from heart failure, and his institute was officially renamed the Niels Bohr Institute in 1965.
And the Bohr intellectual dynasty continued right into the next generation. His son, H. Bohr, who was with him during the Mosquito Flight and worked on the Manhattan Project, also won the Nobel Prize in Physics in 1975.
A remarkable continuation of their scientific contribution. And we should remember that range of interests remained. Another son, Ernest, followed his uncle Harold into Olympic sport, playing field hockey for Denmark in the 1948 Summer Olympics. The family truly represented the integration of mind, body, and philosophical rigor.
So to synthesize what we've learned from these sources, Bohr's life was really defined by the concept he created, complementarity.
He was constantly navigating and reconciling necessary contradictions, the practical demands of the gold medal competition and the abstract demands of quantum theory, the classical worldview and the probabilistic quantum reality, the ideal of scientific neutrality and the terrifying demands of global security during the nuclear age. He was comfortable with paradox because he saw it as the essential, defining feature of a complete reality.
What stands out most is that Bohr didn't just accept paradox. He actively bridged these worlds. He was the connector between Rutherford's atom and Planck's quanta, between the old guard of classical physics and the young radicals of the Copenhagen school, and between the secrecy of the atomic project and the moral necessity of an open world.
That ability to bridge, especially between the quantum and the classical, brings us back to his core philosophical demand, which is the idea that our language constrains our description. Bohr insisted classical concepts, position, time, causation, are absolutely necessary to describe experimental outcomes.
Arguing that our ordinary language, refined by classical physics, is the only means we have for communicating what we observe about the quantum world to others.
Exactly.
That sets up the most provocative thought based on his work. If our language defines the limit of what we can communicate as scientific truth, does the progress of physics ultimately depend not on developing better mathematics or faster computers or finer measuring tools, but on developing entirely new ways to speak about and thus conceptualize the phenomena we observe?
Could the next truly radical revolution in physics require the invention of entirely new, non-classical words and concepts to break the linguistic constraints Bohr identified? It leaves you wondering, doesn't it? If Bohr is right, if our language is the cage, what's the next great leap? Is it better math? Or do we need to invent a whole new way of talking before we can invent a whole new way of thinking about reality?